Hello, and welcome to this GIE Media Manufacturing Group Lunch and Learn webinar. I'm Eric Brothers, Senior Editor of Aerospace Manufacturing and Design magazine. During this session, we'll have two polling questions attendees can answer. Watch for them. The results will be revealed at the end. This half hour is devoted to a closer look at 5-axis machining with circle segment end mills, sponsored by Amugi Franken USA, a leading manufacturer of precision taps, thread mills, drills, end mills, tool holders, clamping devices, and rotary tools. Amugi's recently expanded West Boylston, Massachusetts facility includes a technology center with a machining and tooling demonstration showroom and classroom, tool manufacturing and cutting, reconditioning, and more. Application engineers are available to provide programming assistance and process recommendations. Our presenter, Evan Duckinson, has more than 12 years of technical and engineering experience in metalworking manufacturing, most recently as Amugi Franken USA milling and application specialist. You may also ask questions at any time by using the Q&A button at the bottom of your screen, and we'll get to as many questions as we can after Evan's presentation. Now here's Evan.
All right, thank you everyone for joining us for this presentation. So we're going to take a closer look at 5-axis machining using circle segment technology. And we're just going to go over a lot of the idea behind circle segment tools, the different shapes, and that kind of stuff that we offer, and then some examples of some of the parts that we've done before. One bad example of something that would not work for circle segment tooling and stuff like that. So let's get into it. So before we get into the different shapes of the circle segment tools, I want to go over what the circle segment tooling really means and why we want to use it on our parts. So first, circle segment. It's pretty straightforward. It's the segment of a circle on a tool. So you can see all four shapes here. Each one of them has a segment of a circle or a radius or an arc or whatever you want to call it on the tool. If you zoom way in on it, there's a radius there, right? All of them have different radius ranges, ranging, all the way up to 1,500 millimeters. But they're all a radius on the tool, and that's where we get the circle segment terminology from. It's just a segment of a circle on this tool. So you're using a larger radius on a relatively small shanked tool to increase your surface finish and decrease your cycle time. So there's 4 different shapes that we offer here: taper, oval, lens, and barrel. We're going to get into what those shapes are and where to use them in just a second. But just as a side note, we developed this technology with Hypermill, who's made by OpenMind over in Germany. So OpenMind and Amugi got together and said, how can we make finishing faster? 3D 5-axis finishing faster. And they came up with this technology. So Hypermill built the toolpath, Amugi built the cutters, and we put them together, made sure they worked with each other and everything like that to decrease cycle time and improve your surface finish. So the first shape I'm going to go over is my favorite shape. It's the taper form. In my opinion, it's always the tool you start with. It's going to give you the best surface finish and the most cycle time reduction out of any other shape. And the reason for that is it has a large radius compared to the shank diameter. So we have shank diameters from 6 to 16 millimeters. We have a cutting radius from 50 to 1,500 millimeters. So a 16 millimeter shank tool with a 1,500 millimeter cutting radius on it. And because of this, you're gonna, be able to do a very, very large step down. So you're going to decrease your surface or your cycle time significantly, and your surface finish is going to be really, really nice, really smooth because of all of that material removal you're taking off in one pass. Because these have such large radiuses on them, they are locked to a certain tip angle. And that tip angle for the taper form A is 12.5 to 42.5 degrees. And the taper form B, which is more end cutting rather than side cutting, is 60 to 70 degrees. Okay, so the taper form A, I would use on this structural component here. You can see where the arrow is pointing. There's straight walls. Not a lot of people would think you would need to, finish straight walls like this, but because they have such tiny little corner radiuses and they're so deep most often, you can't get in there with a regular tool to finish this entire wall at one time. So the normal way is just swiping back with a ball mill. But with the taper form, you can do this very, very efficiently with very large step overs or step downs and really finish those very, very quickly. And then the taper form B, I would use for more, end cutting, more floor finishing or something like that. The next shape I want to go over is the oval form. So the oval form, in my opinion, is the most versatile shape. And that's because it has a relatively small cutting radius compared to the taper forms. So we have shank diameters from 6 to 16 millimeters and a cutting radius between 50 and 95 millimeters. And because of that, this tool can be tipped to many angles. It's not locked to a certain angle like the taper forms are. And this lets it, get into some smaller spaces or spaces that the taper form just couldn't fit into. Something like this part where, you have different geometry that is getting in the way of, some of your surfaces that you want to finish with your circle segment tool and stuff like that. The taper form is going to be locked to that certain angle. You can only get into certain areas, but with the oval form, you can tip it a little bit more. You have a little bit more freedom and flexibility to get into those areas, but still achieving a very, very good surface finish with a lower cycle time. The third shape I want to go over is the lens cutter. So the lens cutter is really only for end cutting. It really only has geometry on the end of the tool. And because of that, it has a little bit smaller of a cutting radius than the oval form. So it's a 4 to 10 millimeter shank diameter range with a 6 to 25 millimeter cutting radius range. So normally it's 2 to 2.5 times the shank diameter is the cutting radius. And, mostly used for floor finishing, like this tire mold. Those surfaces that the arrow is pointing at would be perfect for a lens cutter. Really get in there and clean that out quickly. Otherwise, you would have to go in with a ball mill and really pick away at that very, very slowly. The last shape I want to go over is the barrel form. I think everyone's seen a barrel cutter before. It's nothing new, really. But this was kind of what sparked this technology was, hey, let's look at the barrel form and let's modify it. Let's improve on it. Let's put a different radius on it. Let's tip it at an angle. Let's put it at the end of the tool, whatever it may be. But because this tool is really only used for undercuts, we only offer one size. It's the 10 millimeter shank and a 50 millimeter cutting radius. And you can see on the right here, that picture, that outside shape there actually has an undercut. It's at a concave surface. So that's really the only time you would want to use the barrel form. And because of that, it's, lesser used than all the other tools. A few years ago, we expanded our line of circle segment tools. We heard our end users say, hey, what if you have this? What about this one? What about this, right? And we expanded our line to help those end users out a little bit more. So these tools we created with more flutes. So we essentially doubled the flute count of the taper form and the oval form tools. So where you had 2 flutes, you have 4 flutes. Where you had 3 flutes, you have 6 flutes for the most part. And obviously, this will let you cut harder materials, up to 60 Rockwell. You have more flutes in the cut at one time. You're going to have a more stable cut in those harder materials, and you can achieve higher feeds. Obviously, you can cut faster with more flutes with the same chip load. And then, excuse me, and then with the same expansion, we came out with these tools that have a roughing profile on the tool. So this is actually a modified version of the oval form. It has a flat bottom instead of coming to a ball. So it's a very rigid, very solid tool. And you would think, well, why do we need a roughing profile on a finishing cutter, right? Well, this is for semi-finishing tools and mostly for thin parts like blisks, blades, and that kind of stuff. Like this blade here. So this was a blade that I did for a demo a few years ago. It was a titanium blade. And after roughing it, we had a lot of material still on the blade. You can see on the left here, there's all that material there. And it's an inconsistent amount of material. You know, if you were to just take that part and finish it, try to finish it with a taper form or an oval form or something like that, you would get a lot of deflection on the part because it's so thin. You would get a lot of deflection on the tool, and because it's an inconsistent amount of material, you would actually see that in the finish, right? You would see some ghosting, you would see some different surface finishes depending on if you're cutting a little bit less or a little bit more material at that time. But with the roughing profile circle segment tools, you can semi-finish that blade and give it a consistent amount of material for the finishing circle segment tool to then take off and give you a really, really nice finish. So you can see that on the right here. There's still about 10 thou or so on that blade after the semi-finished tool. And the taper form that's going to come in after it is going to clean it up, look really, really nice. And with the expanded line, you know, with the multi-flute tools and the roughing profile tools, we expanded what materials we can cut with these tools. So, you know, with all of these tools, we can pretty much cut all your materials. You know, some tools are better at cutting certain materials than other ones. You know, the multi-flute designs aren't going to cut your aluminums and your plastics and stuff like that all that well, but that's where we have, you know, the lower flute count tools for, and vice versa. You know, the multi-flute tools are going to cut your higher hardness materials, the 45s to the 60 Rockwell materials, where the regular 3-flute tools are going to cut them, but not as well. And you can see everywhere we have a black dot means the tool is very, very suitable, the perfect choice for that material. Anywhere we have an open dot means it will cut it, but a different circle segment tool is probably a better choice there. And then we have our CAM softwares. So one of the biggest hurdles to get over is, how do I program these tools, right? And the CAM softwares that support these tools actually have to have support for the geometry and the tool paths and everything like that to actually utilize these tools. You can't just throw it in any CAM software and, you know, put just a raster back and forth, a zigzag tool path on it, because, you know, you're not just using a ball mill, you're using a segment of a circle, and there's a lot of calculation behind that. So obviously we developed the technology with Hypermill. Mastercam is, you know, right there next to them with their functionality. And then, you know, listed here are just a few of the other softwares that support the technology as well. There's more. I only included, you know, some of them. And here we have our demo room, or our tech center. You know, we have 2 Hercos, we have a 3-axis Herco and a 5-axis Herco in there, and then we have a Grobe 550 G550 5-axis machine in there as well. And we can do all sorts of test cuts and demos and stuff like that in there, to get some real world data. We can record video and everything like that and send it to, an end user. So a lot of people ask me, why use circle segment tools over ball mills, right? I always say cycle time reduction, surface finish increases, and everything like that. But these two videos show that really, really nicely. And there we go. Now they're playing. So on the left here, we have a 1/2-inch ball end mill, and on the right, we have an oval form. So you can see that both tools are just doing, a zigzag motion here, and they are both doing the same step over of a 1/2 millimeter. And you can see the scallops you get on the ball mill. You can see those very, very clear. And then on the oval form, you really can't see them. They're still there, but they're much smaller, much slower. And you really won't be able to perceive them all that well. So it'll look like a much, much smoother surface, and it will measure to be a much, much smoother surface. And because of that, then you can change your step over to a larger step over and achieve the same surface finish as you would with a ball mill with, maybe 5 times or 10 times the step over size. And this is a nice video that we did of, the real world version of that graphic. So on the left, we have a 10 millimeter ball end mill. On the right, we have a 16 millimeter circle segment tool. And you can see just how much faster the circle segment tool is finishing this concave shape here. And the cycle time of the oval form was 36 seconds. And for the ball mill, it was a little over 6 minutes, which is a 90% cycle time reduction. So obviously a huge, huge savings. This is a nice graph that I put together for a customer in the past. And, it just shows you how much savings that you can get out of a taper form, a circle segment tool. So the cycle time in the orange there, you can see just how much cycle time reduction we're going to have. In the black here, you can see the tool cost. Now, obviously, these tools are going to cost more than your standard ball mill. There's a lot more engineering. There's a lot more grind time and everything like that in these tools. So, this tool costs about double the ball mill. But when you factor in the cycle time reduction, the tool cost, that your tool life increases and everything like that, you can see in the gray here, your total cost for this taper form is quite small. And then your total cost for the ball mill is increasingly bigger, with your machine cost per hour and everything like that factored in. And in this application, we got about 80% cycle time reduction. And that's usually what you can bet on, about a 70 to 90% cycle time reduction overall. This is the same part that we were looking at before with the blade. So this is just a nice graphical representation of the tool path of, a ball mill versus a taper form. So we have a 1/2-inch ball mill, and we have a 16 millimeter taper form with a 1500 millimeter radius on it. Just as a side note, you can see those 2 gaps in the tool path for the taper form. That's actually, it's not a gap in the surface or anything like that. It's just how Hypermill showed the tool paths, because they are actually 3 different separate tool paths, but they do overlap, and it will create a nice smooth surface there. So the step downs, the ball mill, a little bit over a 6th step down. The taper form was almost an 80th step down. But both of these tool pass will create the same scallop height of a 0.5 micron. So you will get the same surface finish out of both of these, but obviously with over 10 times your step down, you'll get a huge cycle time reduction. And that reduction is from 1 hour and 53 minutes to about 21 minutes. 81% cycle time reduction. And these are actually real world values. I actually took both of these tool paths and ran them on our machine. And this is the actual cycle time I got off of the machine. So this isn't from the CAM software. It's not, the calculation that's probably a slightly incorrect or something like that. This is actually off of the machine and actually what it did. And I love this slide. So at the bottom here, circled, you can see that's the actual part. That's the blade there. Now this part is about 6 inches in diameter and about 8 inches tall. And then this huge massive thing above it, that's the actual tool if the taper form was a ball mill, right? So that taper form has a 1,500 millimeter radius. So this is a 3 meter or a 3,000 millimeter diameter ball end mill, right? So it looks absolutely ridiculous. Obviously, you can never put that tool on that part and actually cut it, but this is essentially what the taper form is using to cut this part. Just a very, 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 very small segment of that tool, right? And then here's the final product. So nice picture of the part. Every surface was cut with circle segment tools. The blade, the platform, and part of the base were done with that 16 millimeter, 1,500 millimeter radius, 12.5 degree tipped taper form. And then the other blade base surfaces were done with a 60 degree taper form B, which I believe has a 500 millimeter radius on it. And you can see just how beautiful those surface finishes are. Very, very shiny, almost like a mirror. And obviously that was achieved with the circle segment tools, but I have to give some of the credit to our Fpc holders as well. We always suggest putting our circle segment tooling in our Fpc holders. They hold just a little bit better and just a little bit stronger than your heat shrink holder or something like that, but they also give you like some dampening properties like a hydraulic holder or something like that would give you. So they're kind of the best of both worlds, and they increase that surface finish just a little bit more with the same tooling. So this is an example of a part that I would not suggest using circle segment tooling on. And the reason for that is this part, it's about 4 inches in diameter, maybe 3 inches or so. So it's, it's fairly small. There's a lot of undercuts on it. And you would say, well, Evan, you said you can use a barrel form for undercuts. I did. But these undercuts are just a little bit too close to all these other surfaces. There's a lot of intersecting surfaces with these little corner radiuses and everything like that. So you would be able to use a circle segment tool for a very small amount of these surfaces, but then you would have to blend it all with a ball mill, right? So you're going to have some circle segment finished surfaces and some ball mill finished surfaces, and then you got to blend the two, and that can be a real pain. So what I would say is you're really not going to get the cycle time reduction out of the circle segment tools on this part, mainly because you're going to have to do all that blending, and the blending takes a long time, right? So I would stay away from circle segment on parts like this. So this is an end user part that we did a little while ago. So it's some sort of cover enclosure type part, and they asked us, hey, can we finish the top and the bottom surfaces with circle segment tools? So we took a taper form. It was a 10 millimeter shank with a 250 millimeter radius. This is a 20 degree tipped tool. And we did a step over of 80 thou feeds and speeds right out of the book, and the cycle time was about 12 minutes. Then we took a ball mill, half-inch ball mill. We did an 1/8 step over, speeds and feeds right out of the book again, and the cycle time was 50 minutes. And again, these two tool paths will create the same surface finish, the same scallop pipe, right? So everything else the same, but your cycle time is down from 15 minutes to 14 minutes. And then the inside, so we tried to get a taper form or an oval form to work inside here, but because of the walls, the exterior walls of this part, we just weren't able to get it in there for it to make sense to actually use that tool. So we used a lens cutter. This was a 6mm shank with a 10mm cutting radius. We did a 20 thou step over, and the cycle time was about 40 minutes to do the inside of this. Same thing, we took a 1/4-inch ball mill. We did an 8 thou step over. Cycle time was 100 minutes, and the same thing. The scallop bites would be exactly the same, but you can just see how dense that tool path is. You can't even see through it, right? That's a lot of lines, a lot of back and you know, and it's going to take over double the time that the lens cutter would take. And then I had an end user call me and say, how do these tools work in 718 Inconel? And I had to tell him, I don't really know. I hadn't had that question yet. I hadn't used these circle segment tools in Inconel before. So I took this tool, it's a 12.5 degree, 16mm taper form with a 1000mm radius. And I found a piece of Inconel we had. It was about 100mm diameter. And I just did this tool path, just kind of, you know, swiping at this material. I did 100 SFM, 200 thou step down, 1.8 thou per tooth, and 4 thou depth cut, you know, per slice. And here was the final product after doing 20 passes. The finish was very, very smooth. You know, you could barely feel any kind of machining marks or anything like that. And the finish didn't change from start to finish, right? So the tool held up really, really nicely. There was no degradation of the cutting edge or anything like that. And you can see that in these microscope pictures here. So, you know, this is on the right 200 times the, 200 times magnification. So each pass was about 30 linear inches, and then 20 passes, you have 600 linear inches of cut, and the tool was really worn, you know, barely at all. It was just breaking through the coating, and, you know, we had to put it on the microscope to really even see any wear. And if I had to put, you know, a number on it, the wear was about between 5 to 8 microns, you know, so very, very little, almost no wear at all. So that's the presentation. Here's my contact information. Feel free to contact me at any time, and then we can open it up to questions.
Thanks, Evan. I think we'd like to take a look at the polling results if we can. So are you currently doing or planning to implement 5-axis machining? 77% of you answered yes, 23% answered no. What are some of the current challenges you're facing with milling applications? It's a multiple choice question. 65% of you said you need to reduce cycle times. 29% need to generate cost savings. 12% have to deal with tougher materials. And the largest number, 71%, said overall tool performance and reliability. So we have time for just one question, it seems like. So Evan, what programming hints can tool engineers give to programmers using NX or CATIA?
Yeah, that's a really good question, actually. And, you know, my first suggestion would be, and I went over this in the presentation, always start with the taper form it's going to get you the best performance and the best cycle time reduction. So try that one out. And if you can't fit it into a spot or anything like that, then go over to your oval form and try that out. Also, I want to mention just real quick, we do offer programming support and application support for these tools. So, if you were able to send us a 3D model, we can put it into either Hypermill or Mastercam. Those are the two CAM softwares that we support here. And we can actually program the part, pick out the tools, the feeds and speeds, the tool paths, everything like that, and, give you a presentation on how we would do it. And like I said, all the feeds and speeds, your cycle times and everything like that. So then you can replicate that in whatever software you may have.
All right. Well, thank you. That's all the time we have for this part of Lunch and Learn. Thank you, attendees, for your attention and questions. And thank you, Evan. Amugi Franken
Thank you.
USA is a leading manufacturer of precision taps, thread mills, drills, end mills, tool holders, clamping devices, and other rotary tools. For more information, visit www.amugi.com.